Hello everyone. Today I want to talk about how to uh, create a linear transconductance or have a linear behavior in CMOS. So we know CMOS is a little bit not oh, linear. You know what? You know why? The reason is I want to add a AC source and a DC source. So we know the relation between the output current is kind of with gate source is quadratic, so it's and so this makes that when we have a small gate source, we would have like a huge output output current. However, it is quadratic. It is not um, in terms of nonlinearity is not as much as bad as uh, bipolar transistor, but still. So uh, so the relation is nonlinear, and we know the reason for the nonlinearity is gate source, because with the small gate sources we have huge IDs, we have huge currents. I want to mention this term has just you have second order harmonic here, but we know in short channel this factor is not 2, and it could be 1.5 and or other stuff that may introduce other terms of nonlinearity. One other thing here, very good point to mention, is the way that you can reduce nonlinearity here is you can increase the bias, because at the end your output current has a like a has a relation between the AC part and the DC part, and we know the DC part is always constant, and this is the AC that creates the nonlinearity in mostly in large signal mode, not mostly in large signal mode, and so the point here is to increase so the gate source would have a less portion of the input signal, and so the nonlinearity would be less. You can there in the books they kind of find that by using equation and stuff, but you can see that here and understand that easily with this method. And another way to think about that is when you increase gates, or you actually increase your overdrive, and we know in higher overdrive we have more linear behavior, because we push our device uh, through strong inversion, and in a strong inversion you have a more linear behavior, and actually this equation is more authentic in strong inversion. uh, uh, so I want to delete this. Okay, so how to make this guy more linear? So we know the easiest way is source degeneration. So use source degeneration, add a resistor here called RS, and then now the AC signal is divided by the nonlinear device and a linear, almost linear uh, component, which is a resistor. However, we know this kind of it's like a feedback mechanism. So when this goes up, we have more and more current, but the thing that is happening is the voltage over here also increase, and it kind of uh, squeeze the gate source. I want to say that. So when this gate is increasing, when the gate is increasing, so the transistor like to have more and more current, and it's more and more nonlinear behavior. And if it was like that, so it continued to have a bigger gate source, and as I mentioned, the gate source is the the source of nonlinearity. We can say it like that just to remember. But in this case, the resistor kind of work as a feedback, increase the source, and try to have a more constant gate source variation. I want to say it like that. In this case, go up and up without any concern, and go bigger and bigger. But here the current come back and kind of control the gate source, squeeze it. However, it's not that much good. We go back to that later in this video. Another not problem, but good observation that in some cases could be a problem is when you have a system with a negative feedback. This is a negative feedback, so you have I don't know, the amplifier, and then you have a feedback here, and feedback is like negative, and we can write down the equation and stuff that even in like system with as I defined with like relation between ID and gate source, let's put it like that, is quadratic, and you have only second order harmonic. You can show that easily with just put down the equation and stuff in this feedback system. You can see you will have third order harmonic and third order nonlinearity in your system with the feedback. However, feedback always suppress the second order, but it kind of intrudes the third order. In some cases, might be, mostly in RF, might be a concern based on your application. So I introduced some sort of a feedback to reduce the nonlinearity, but another way, a smart way to do that, to suppress nonlinearity, is to divide nonlinearity between more gate sources, or not nonlinearity, divide the signal between more gate sources, so each gate source will have less portion of the input signal. And the way to do that is to use the beautiful differential circuit, which all of us really like. And so then your input signal is divided between two sources of nonlinearity, and each one will have a smaller portion compared to this configuration. They receive a smaller portion of the signal. So this is the way to look at it. You can write down the equation also. This is another way to look at this phenomenon, and it's a very good way to look up the books and papers and see the equation and how they define the nonlinearity. But here I try to use a method just to remember stuff, not go deep in the mathematics. Another reason that we like this configuration regarding nonlinearity is if you have a x and you always have minus x as a signal, and you have a output y and y prime, so you can define a system by in this way that I'm going to show. So you can define it, this mathematically. Alpha 1, not x1, sorry, this is not x1. Oh, so it's x plus alpha 2 x2 and alpha 3 x3. As a quiz for you, what do you think about alpha 3? Is it negative? Is it positive? So just, I know you know the answer. And we can define uh, y prime as alpha minus alpha x, because we are defining this part, and alpha 2 x2, no negative for this one, and then sorry, then alpha 3 x3. And if you kind of take a differential output from the circuit, and you subtract y by y prime, you will see that these two terms, I want to show it in red or something, these two terms will cancel out. So we know, this is a very good thing to remember, with the differential circuit we will not have a second order nonlinearity, and the only way to see it is by mathematics. So as I mentioned, one way is using differential, another way is to use degeneration in the source, and the third way is to mix these two and like have a circuit like this, and add the resistors over here. So you have both the effect of the differential and also source degeneration. The problem with this one is if you have a high amount of current, so you kind of sacrifice your output swing by using this resistor. So if you have this one in differential mode, this is RS, and this is, like, we call it, for example, VID1, and so by having this one, so a portion of your headroom is kind of is taken by the source degeneration resistor. Also, there is a variant of this circuit which is maybe more popular. Sorry. So there is another variant of this, is to, like, using one resistor and put two tail over here. If you compare these two with each other, you will notice that so we don't, because of the symmetry in the differential circuits, so in the DC or in common mode, the voltage over here and here are the same, so no current will go through this one in differential mode. However, in the AC, we know the behavior is the same as before, and the middle of this resistor, let's say, is a virtual ground. And in differential mode, I think I mentioned differential mode, this part goes out and this part goes down, and you have a current from here, and the rest of the story. So go back to the common mode, or in DC mode, the voltage over and here are the same, so no current will go through this part, and you wouldn't have the problem of headroom that I mentioned. And also we know if the current is not going through this resistor, it wouldn't have any effect of the offset in our final results. There's another way to make the system more linear, is so use the RS and everything as a source degeneration, make it differential, current tails, uh, and then you can add two op amp uh, like this, minus plus, and let's call this v1 and v2. And here you can see you will have like a source follower configuration. Now when we like source follower, as I mentioned, when the current is increasing, when the gate source is when gate is going up, so the transistor like to have because it will have a greater amount of current, so it's kind of will have a greater gate source, so source will not follow the gate, and we will have some sort of a nonlinearity. And in this configuration, the source will follow the gate and they stay the same, and the current that go through this one is kind of v1 minus v2 by r, so it's a linear behavior. I hope I explain it in a way that you can understand. And we know using op amp and stuff, it will have its own problem. Another way to make oh, sorry, that was my phone. Another way to I'm trying to put it on the mute, so it's on mute. Sorry about that. Another way to make it more linear without using uh, op amp is to use a local feedback. This one is very popular and a little bit not easy to understand. But so you use two PMOSs here. Sorry for my drawing. And these are VDD, and this is rest of the circuit. So one way to make it more linear here is to use a local feedback. How this works, as I mentioned, you always need to have some sort of a configuration that source follow the gate in this scenario. So in like something like this, you will see then when the gate is going up, so the source at the beginning goes up same as that, but when the current is increasing, the source does not follow that much. And so also if you review your knowledge about common drawing, it's the same phenomena there, and the GM going to be bigger and bigger, more non-linearity and stuff like that. So we always like to have a configuration with that source can follow the gate. This is just like a point to remember. It's not the whole story, it's just one point to remember. And with a local feedback, you have something like that, like this. This is the PMOS, and what is happening is same as this guy, but by using this you kind of force to have to source follow the gate. Also for the last one with the op amp is the same configuration, so when this guy go up, this one goes down, this one goes down, and sorry, this one goes up. And what is happening, you can see that this with this try to uh, push some sort of situation that source can follow the gates and kind of suppress the nonlinearity. So yeah, this was some blocks that will be useful. I just want to mention that you can then, after using this, you can copy the current, use like a current mirrors and stuff, and put the R over here, do the same here, put the R over here, and take the take the differential output as current or whatever you want. It is good to review some paper if you are interested. Just search linear transconductance, or look to the books, and there are main references are in the books. You can review this stuff also with too much more explanation and the mathematics and everything behind it. Also, you can make these parts cascade to remove the effect of channel length modulation, and you will see lots of iteration and lots of variance about this kind of a circuit. Thank you for watching.